Good morning, ma. All are present now.
No one joining.
Okay. 39. We are supposed to have 61, na? 59.
Maybe 59 or 60. That.
Okay. Then how many minutes? 2 more minutes, I'll wait.
Ma'am,
Yes, ma, we'll start. All are here.
ma'am, I have question. Uh,
Yes.
you are our project guide, so when will we start our project?
Yes. So probably today after the class, how many of you have to work with me? Jay Kishan and
Me.
who is that me? What is the name?
Ma'am Priyasha.
Okay, Priyasa. Then Chandan Kumar. And that's all, right? How many of you? Yeah, Somnath. Okay. Okay, so after this class, you four stay in the line. I want to discuss. Others may log out after the class. Okay. So we'll see. Now it is 52 students. Okay, let us not wait. We will start the class.
Okay.
Yeah. So in the last class, we have seen until this force field expression for a bonded and non-bonded. And now we are just coming into a real thing. Okay, so what happens is we are going to work on the energy variation with respect to X. See, if you see your previous this thing, the bond. Okay, this is X0 minus X. Even though it is B0 minus B, it's a position dependent. So you have a variation in this parameter. Every variation in the parameter will be reflected in the total energy. Similarly, you have an angular variation which is also associated with a bond variation. Okay, so a positional change again will reflect. So R is there, R is here. So everywhere indirectly, directly or indirectly, the R is there. Okay. So what happens is if you are going to plot, yeah. Oh, the same is there. Okay. Okay.
Ma'am?
Yes.
Yeah, I'm requesting to Sadia to please start the recording.
Yeah, no problem. Okay, after 20, what happens? It is not moving to the next page. What is this? Let me see. I'll go like this, down to from the right. Then I choose this. Like this. Okay. And I will open a new one. And then share on. So it will be shared with me. Okay. So this also. Fine. So so now what is the issue happening with this calculated terms in the bond energy, dihedral energy, torsional energy, angular energy. Then the non-bonded interactions, like Coulomb interactions, van der Waals interaction, hydrogen bond interaction, dipole-dipole interaction, what happens is that there's a variation associated with the position. So as long as there is a variation associated with the position, the energy is varying, correct? So I'm only plotting this graph with R versus energy. Okay, so what could be the energy? Because when we are drawing a structure, okay, suppose if, for example, if I am modeling one protein or one benzene structure, okay, in the screen I may draw like this, okay. Okay, what will happen? I have to put one C here, proton here, everything I'm putting. Okay, this is very vague. For this, what I should represent? I should represent the charge of a carbon here and the charge of a hydrogen here. Okay, this carbon has a sp3 hybridization. Okay, so everything I'm going to present. But ultimately, when you see the benzene in the real native state, will it be like that? Normally, it has to be like this. Okay. So when you optimize this, when you refine the structure, what I have drawn, when you refine the structure, and if you do some kind of preliminary operations, which I will be explaining in my following classes, and that time the structure will be like this. Okay, so this is a planar because this is a partial bond, and this is a planar. So what happens? This is a stable structure. Okay, okay. So the stable means the interaction between C and H is comfortable. The interaction between C and C is comfortable. All over the entire benzene ring is in a comfortable state that we say is a stable state. In this state, it will get the minimum energy because there is no disturbance by any of the atom. All have settled in their own position. Nobody else is disturbing them. So it will be sitting in its own position without any disturbance. Okay, it is like you are occupying your own chair in your home and nobody comes and disturbs. What will you do? You will remain in the chair. You will not work. There is no need of external energy. So your energy level will be normal. That is your body energy level. But if you are getting up, you are fighting with others, your energy level will go out. That time, your structure will not stay as it is, right? So there is a disturbance. Similarly, you can also imagine, so there is a stable state which belongs to this one, where the molecule comes here. But we have drawn somewhere where everything is distorted, like there is no proper sp3 representation here, there is no proper bond here, there is no potential of hydrogen here. So what is, it is like, will be very high. The energy is with the most of steric interactions. That is, unwanted disturbing interactions will happen. So this structure will belongs to a high energy level. So the molecule will be, when you minimize or optimize, the molecule will come down. Then what happens? It goes and it goes like that. So what happens is, there is a region where the molecule covers a wide range where suppose a molecule can relax. Okay. Sometimes wiggly wiggly structure, if it shows, it can go fluctuation and it can, the energy can go like this. But to some extent, even if you do this, there won't be any change. And to some extent, if you disturb the R, it will be high. This is an unwanted region. This is also an unwanted region. We are worrying about the region where the molecule is relaxing. This is the region where the molecule is in the stable inert state. It will be undisturbed state, highly stabilized state. So every time when we plot this, here this is one choice only. I have plotted only R. I can plot even the same energy level with theta or with phi or your Coulomb energy, whatever energy parameter I can do it. But if I take a generally R, I consider every R which is accounted in the non-bonded as well as bonded. So there is a variation. The energy will not be a single value. It is a function, continuous function, which is established by the difference in the R. You understand? Students, you guys understand this? Okay, only one yes. Others are sleeping, huh?
No, ma'am, understood.
Okay. Okay, you understood, right? No answer. You didn't understand? Okay. How many of you didn't understand this? This we have been discussing this for the last 2-3 classes. Why I don't get any sound? I will do that. Okay, why you guys are keeping mum? Why there is no sound? Okay, fine.
Ma'am,
Yes.
um, Ma'am, here we are doing the energy minimization for the particular compound, right?
Yes.
So, ma'am, how can we apply this in while doing the modeling? When we do a molecular modeling, is how the compound is differentiated, whether it's minimized or not?
These are all the things we will be studying one by one. But for the understanding of this energy variation, I am explaining. The unit 2 will talk about everything, whatever you ask now.
Okay, ma'am.
Yeah. Okay. So now the thing is that there's a variation. So what happens is that the maximum point in the energy level, the minimum point in the energy level, the unchanged plateau region, these are all some of the characteristics. If you see some energy, high energy level, you won't prefer the structure because that may belong to some other unwanted. If you are going with a very, very least negative energy, then you will take this as the stable state of the particular molecule. Okay. So what happens is, if you are plotting, okay, this is for the force, don't worry. But if you are plotting the X and maybe the force or the energy, whatever it is, a molecule may exhibit some transition states and it will give very flexible in the energy level within some acceptable region. It will not go too much. Okay. So what happens is you have minimum, minimum, minimum. But which minimum is the least minimum? For this one. So we term this as a global minimum. And what about this one? This is a maximum, maximum. This is the global maximum. These are all the local. Because every local space, the molecule will try to accommodate. So it will try to accommodate, then get some disturbances, or it will move to some other conformation which is higher energy than this level. So there is a travel, there is a behavior of this molecule like this. It is not only like this, the pattern may vary, but you will have definitely a minimum state, a maximum state, or in between the regions you will encounter. Then we see this in the unit 2. But coming back to this, the entire characterization or the representation of the force field, now we are using some standard template which is already derived. So this is the research of from 1990 onwards. Okay, I think 1984 also article there. So more than 2-3 decades, and we are working on this force field development. And now these force fields are named under some category, and they are being used for the molecular dynamics simulations. So there are so many force fields. Today I'm taking one such example, that is the amber force field. Okay, amber force field. Maybe if you use some kind of simulation packages like Gromax or Gromos or Tinker or Amber, whatever it is, the software has to use some force field. Okay, so the force field name, what we are going to see is the amber. This is one such example. So what do you mean by amber? If I say, okay, I'm going to use this amber, means this amber will have also a components of all the bonded thing and the non-bonded thing. Okay, so when you have all the bonded and non-bonded, the priority is first how you are representing individual atoms actually. So, for example, if you take a carbon, the carbon staying as a terminal one, the carbon connected to another carbon, the carbon connected to aromatic ring or sorry, any other. So the carbon which has the double bond, okay, then everything, the carbon connected to 5-member ring. So everything has its own atom type. These are all the atom type. Okay. So if we cannot simply put this as a C, everything is distinguished. Similarly for the nitrogen, this I am talking about the amber. So sp2 as it is, and amide and Na where it is, Nb, Nc, N plus, N2, N3. So there are so many atom types which is defined in amber. Maybe some other force field also you can see most of the thing, but there may be some differences. Okay. So the first thing is that you have to identify or you have to define the atom types. So this goes like with all the elements in organic this thing. So you have to represent And this is, you can simply give a read. There is no need that you have to study this and everything one by one. The next point is, okay, we addressed the atom. Now the next thing is that each atom we have a bond. So what happens? We are going to the equation. What is the equation? B0 minus B the whole square, and we have a force constant. So when there is a force field for this bond, you have to have a force constant and this parameter, the standard B, right? So let us come here and we see the bond. For example, when this C interacts with this Ca and this C interacts with Cc, so you can find out Ca, Cd, Cm, terminal carbon, Cn, nitrogen. These are some of the examples. So there is force constant which is already been calculated using the IR spectroscopy. Okay. So this force constant and equilibrium distance is also reported. So for almost every bond you have a force constant and the equilibrium distance. Okay. So you can use this value in this equation and you can sum with the overall bonds and understand the total bond energy. And similarly, you have an angle. So what is the equation of angle? Theta 0 minus theta the whole square. So there is a force constant, angular force constant. So you have a force constant and theta equilibrium value. So everything. What is this making an angle? C, CA, CA, C, CA, HA, C, CB, CB. So these are all the type of this. But you have to choose if a molecule what is there. So you can, I mean the template itself will take the value and use it. Because if you are using a Gromax or Tinker or Amber, any tool software, if and you specify while running the simulation, if you specify then okay, I'm going to use the name of the force field for the from the amber, because the force field name for protein is different, the force field name for nucleic acid is different, and the force field name for any other carbohydrate lipid, that is also different. So you have to specify what exactly the parameter from the amber you are going to use it. So if you specify, that will automatically take these values and run the simulation. So you have a torsion, and accordingly you have a potential depth and all and everything, the order of the repetition, periodicity, everything you will find. Van der Waals, we have a R, we have a epsilon. Okay, so everything goes like, what is this epsilon? This is the epsilon, and this. Okay, so you have R, and everything. Okay, and what happens is, once you get all the things, for example, if you are working out one amino acid, what happens? C, it is not C, it is CT. It is not H, it is H1. Okay, so it has its own charges. Minus 0.02 plus this thing. So it is the electrostatic potential of this one. So every by representing with this values and everything, we are trying to understand the electrostatic energy or the charge or whatever. Okay. So similarly, what happens? You have to simply apply these values, or you have to tell the software to use the default values from the force field and apply it to the structure, which is structure, and apply it to the structure here. Okay, we are applying the force field here and we are telling the software to run the force field minimization. So what happens is, we are applying this electrostatic charges here, and we allow some additional steps of minimizing this that we will see later. So once we apply the charges and do some process, the structure will come like this. Okay, this we say that optimization, minimization, that we will study in the unit 2, don't worry. So what happens is, when we are using the charges, what the important thing is that whatever the charges we are calculating, that should be applied over the structure what you have generated. So now the question arises, you have to validate the force field that you are applying on the structure. See, this is simply like every student knows the programming, right? You may say that, okay, the program contains first sentence, the list of variables you will put X, Y, Z in the any program. And in the later stage, what you will say, you consider X is equal to 1, Y is equal to 2. Like that, you submit a value to the variable, correct? So submit a value to the variable. Similarly, you are also submitting the force field to the drawn structure. So you are applying the force field on the structure. Okay. So what happens is, if this force field is the right force field, then when you apply it on the drawn structure, it will automatically take the applied force field and get altered according to the force field. Correct? So it will inherit the native structure or property of a benzene ring, for example, whatever we are doing it. So now adapting the force field by the drawn structure is very, very important. Okay, this is, I'm talking from the position of a molecule. The molecule will look for some parameter which it can adopt. But what I am doing from the outside, I am applying the force field on the structure. So I have to make sure that the force field that I am using on the molecule will be comfortable, perfect, or the right choice. So now there is a question of transferability. What is the meaning of transferability? So the force field that I am applying on the molecule, if it is correct, if it is properly validating, then the force field I supplied to the benzene is correct. Okay, but here the thing is that in this benzene, you may have different carbon, right? Okay, so what is the choice of this thing in the benzene? You have one partial charge associated with the proton and this charge and this charge. But suppose if I take this kind of charge and apply it to some other structure, like here, will it be comfortable? The charge of C here, okay, and the charge of N here will be different, right? And even in the same case, what I'm doing here is, you see that the charge of carbon here will be different from the charge of carbon here, because this is like 4, even though it has a 4 hydrogen bond, it is distributed as a double bond, and single bond. But here only you have a 2 double bond. So the distribution of the charge will be different. So the atom type here in the C is different, and the atom type here in the C is different. Okay, so I cannot transfer the C charge of C from here to here. I cannot. So the transferability is not possible. But in force field simulation, we have to look for the molecule. Suppose if I am drawing or deriving one force field for one amino acid, and this amino acid can be used to all the other the same amino acid in other proteins, then it has a point of transferability. Okay, so this is transferability means you are deriving some force field. Students, you guys are sleeping or you are listening?
Listening, ma'am. Listening.
Okay. So transferability means you are deriving one force field for one particular system. And in that system, if it is anywhere in the environment, and if you are able to use the same force field successfully, then the force field that you derive has 100% value. Okay, but if you are, every time you can suppose you have a what is the peptide which has 3 amino acids, alanine, glycine, alanine. Okay, for example, I am taking. So you are making one force field for this alanine, glycine, alanine. And this sequence, anywhere in the protein, if you are able to find, and the same force field, if you apply, that should get, you should be able to apply it 100% without any error. Then I say that, okay, your force field, what you derived is perfectly suitable with all the system, what is having this alanine, glycine, alanine, tripeptide. Okay, so transferability is important. So every time you cannot generate the force field again and again, but you can have a dictionary of force field which can be transferred to a variety of systems. So transferability mainly determines the perfection in the parameterization. What is the parameterization? Identification of proper KV, proper B0, and the proper range of B. And accordingly, identification of this force constant, equilibrium distance. And accordingly, you have to calculate the necessary charges which is being distributed to make this unit neutralized. So all these things involves as a parameterization. So when we are parameterizing, you can make a general parameterization so that force field can potentially be applied to other similar system. That is what we say it's a transferability. And the gas phase data used for some parameters, that is also there, but this will give some error because we always work in the solution phase because our body is in the solution phase. And if we take a gas phase data and we have to modify it or we have to get converted it according to the gas phase this thing. So there is some chemical part, chemistry or thermodynamics is involved. Let us not worry about that. Okay. So when we are making a force field, the first point is it should be transferable to all other similar systems. And historically, the primary method of validating the parameters would be to either minimize or run molecular dynamic crystal structure. Why we have to do this? Why we are deriving the force field? We have to model a structure. After we model the structure, we have to find out the optimum structural geometry of the structure. That we say is a minimization or optimization. So, first point for a force field is, first point is we have to define the force field. Okay, then you have to transfer the force field to the particular system. Once you transfer it, then you have to optimize. That is, you have to find out the solution of the proper structure, geometry of the structure. That is the solution. That is, we say optimization. Okay, once we optimize the structure, we go with environment representation because the molecule is not a isolated one. So it is in some environment. So we have to represent the environment. Finally, we have to run molecular dynamic simulation. So these are all the flow chart that what we are going to study in MD. So now we have defined, we know what is force field, and now we are trying to learn, in this class we are trying to learn how this force field is being applied. And once it is applied, we will go for the next phase, that is the minimization or optimization. Oh my God. Minimization. Okay. So, or optimization. Once you get a proper geometry, you have to set the environment, that is either with water, counter-ion or whatever, then you can simulate it. So, coming back to this, now this is one of the previous steps that is required either for a minimization or to run MD. Okay. So the deviation from the experimental structure would be taken as a measure of the forgery's adequacy. Now we have to calculate error. You know, some see we have experimental technique, spectroscopic technique. We have a spectroscopic technique to identify everything. And now we know a mathematical formulation using the force field to identify this one. So what we can do, we can understand the method we calculate is really coming closer to this. So there is an involved error analysis. Okay. So you have to go and identify there should be no error. So when there is no error, then the force field itself is adequate to represent the biomolecule in a simulation package. So now these methods are the finest first test, and no need you have to validate the force field because the protonation sites are important and the number of bonding and everything is important. These are the general thing you can go with it. So the thing now I'm saying that I showed some value here, right? This force constant, the force constant, and this I said it is identified, right? The preliminary source for this is where do we get this? Okay, so we have X-ray crystallography. We get the bond distance, equilibrium bond distance. And from there, we have a vibrational spectroscopy and everything. From there, we have the frequency and angular variations. Okay. And some applying these two, we can also go with some kind of quantum mechanical calculation and we can get the dihedral parameters. And if we are able to do with the electrostatic potential calculation, then you can get the charges. And from Lennard-Jones potential, we can go with the non-bounded parameters. So these are all the things which is giving input to define the force field. This force field. Okay, so at the end of the story, what is the best force field? Finally, some force field we have to understand that best suit the energy or the behavior of the biomolecule. Okay, just give a read, nothing difficult, whatever I explained only. So this is the brief of the force field. People started work. Oh, it started working in 1970 because this Weizmann Institute people from Israel, they are the very very intellectual people. They began this MD, and Weizmann Institute still is having its own reputation. Okay, so these people from here, you can find out that force field people developed by Cornell University, and Strega and Mikhail. He's from the. I think after this, there's a charm and the biosim and bromos and amber OPLS. These are all the force field, like amber force field, OPLS force field, bromos force field, charm force field. The charm is defined by this Corpus. He's one of the famous person. There are so many reviews done by this person. Berenson is also very known. And Coleman. My favorite person is the Coleman. Because that guy wrote, made Amber and he very exclusively established research. அம்மா கிளாஸ்ல இருக்காங்க வந்து இருப்பாங்க சரி. So this person is my favorite because like when I joined for my PhD in 1997, I started reading this article. Okay, this is I'm talking about 1997. So that time it was his group was very peak in molecular dynamics simulation. I have also read Corpus. I have also read Berenson. Hagler I didn't follow. I don't know why. And these two people made this Chromos 87 version. Initially, Corpus was working on Charm and Berenson were working on Gromos and this thing. And at the end, they both made this Gromos and 87 with one constituents leadership. You know, these are all the research side that they worked on this. ஆள முடியாது அவங்கள வேற வேலையை படிச்சது. And yeah, the later Gromas 96 came because it is year by year they are updating, because every, see now, why you may ask why there is a different version of the same force field. Okay, every new parameter when they try to incorporate, they put a new version, like how we are now seeing the windows and everything. So everything upgradation, they are putting it every year and give a version. So Amber now, I think it is more not 4. It is like more than, I think 9 or something. What is the Amber version now? Current Amber version. I think maybe if I see this, okay. What is this Amber tools? Amber 20 now. Okay, so accordingly they will have a tools also. If anybody wants to learn slowly, you can come to this website, this ambermd.org. Okay, this is the website which made me to learn Amber on my own, to learn the MD on my own. Actually, next to the dictionary for my career, this is the web page. Okay, it is not others taught me. The MD, what I teach you now, it just I learned it on my own. Okay, so you can find these are all the what is that evolution of the history. So you can have the force field. When I say force field, there are some class 1 method, class 2 method, some classification. What is this? The higher order terms and cross terms. See, we have seen the basic representation of the force field. If you are trying to add any other interactions, you can go with the cross terms. Or if you want to develop some additional parameter for the same force field, I mean same what is that component, you can go with the higher order. So every time you are improving the accuracy, every time you are adding some kind of new parameter. Okay, so because science is growing, you get more technology, so you can add more, you can fine tune the parameters. So there are like a classroom method, you can do this. There are some examples adding there. This is molecular Merck force field 1, 2, 3, 4, and effective potential electrostatic force field, and this is a consistent force field. So many force fields are there. And class 2, a very large molecule like a biomolecule, we can use this. See, this is like a chemistry people, most of the people they use this. Here class 2, very large, that is biomolecule we are using, where you are using amber force field, charm force field, bromose force field, etc. See, I give you an assignment to write about amber, charm, bromose, and probably I think there are amber, charm, no need. These 3 itself is sufficient. I think not 3. 5 mark question means, yeah, you have to write. See, I have given something. What is that? MMF, F, and the OPLSA, and what is this? MM2, MM3, MMF. See, I have given some list. But you browse any new article and any current update on the force field. Okay. And there should be some article by Professor Coleman. I think Professor Coleman has one chemical reviews that you should know. Maybe I have it in my other laptops because the current one. Okay, you can download. Yeah, I think this is David Case. This is one of the student of Professor Coleman. And students, you can write down this title. And this is also like they are talking about amber force field, sound force field, OPLS force field, other protein force field. Okay, so you have to understand. You have to read this article. Probably, whatever I have given it, only it is there, and you will be able to understand it very clearly. Okay, why amber force field is very effective for biomolecular system, how they call this charge and everything. If you are really interested in future research, now start working on this. Okay.
Ma'am,
Anyway,
can you share the paper? This one?
yeah, I'm going to do that. Wait.
Ma'am, including slides, ma'am.
Slides I have not shared. I have not shared.
No, ma'am. No.
This
No,
PPT.
ma'am.
Oh, no problem. I will share.
Ma'am,
Yes.
uh, ma'am, when we are going for a molecular simulation, when we use any software, and there are options like whether you have to use Amber or Jam Force field. So when we are doing this kind of thing, so every time we have to go for the validation and all stuff, or
No,
when
no,
we
no.
introduce
No,
something new force field.
already that is being standardized. I'm talking about the initial stages, but now everything is standardized.
Okay, so these are the steps we have to follow when we introduce something new or new force field.
Yes.
Okay, ma'am.
Yeah. So I have posted it, and now these are all. It is not needed. Universal postcode UFF is fine. This one is not needed. Now we have this is not updated, so no need for this. So just go through this, and I'm giving you assignment of writing force field that is being used in biomolecular simulations. And I have sent you articles also. You read this, you know, the important point there, how you are deriving this, and we need a transferability because every time we cannot do it, we have to standardize your force field that can be applied to other similar systems also. So the validation is important. If it is successful, we can say that okay, the force field that we derive is transferable to other similar systems. So this is the content from this class. I think almost we finished this unit 1. Yes? Yes or no? You guys are there?
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am.
Okay. So you start preparing your assignment on this, and from the next class onwards, I will start go with the unit 2. Okay.
Okay, ma'am.
Ma'am,
Yeah.
Okay, ma'am.
So everybody can log out except my project students. Any questions remaining?
yes, ma'am.
Yeah,
Yes,
tell
ma'am.
me, Pooja.
Ma'am, is there a specific structure that we should follow for the assignment? Like, uh, how should we start the assignment with questions or just the summary or how?
I maybe you have, see for the force field there are questions like what is this amber force field? You have to write for 5 marks. If I ask what is this OPLS or what is this charm, okay, so you should be able to write at least for 5 marks. Okay, so I'm giving you, you can take minimum 5 force field, some major 5 force field, and start writing for 1 page or 2 pages, not 1 page or 1.5 page, so that you will have a good content of this one for 5 marks. For this part C also, there's a possibility that I may combine 2, 3 force field and ask you. So you should prepare in such a way that minimum 20 marks you are covering, 20-25 marks you are covering in the assignments. Suppose if you are writing amber, charm, OPLS, and all these things, you write 5 very applicable force fields, and then you send it to me. That's it.
Ma'am, it should be handwritten or Wattpad?
It is handwritten.
Okay, ma'am.
Okay, and every page, the first 2 lines, you should write. See, you use what is the line or whatever, any, maybe I prefer ruled paper, if not other paper also, but your name and your register number, assignment title should be there on every page. You understand?
Yes, ma'am.
Yes,
Every
ma'am.
every page you should have it. Okay, and you put margin left and top. Above the margin, you write your name and register and the assignment title. Then below you write. Okay?
Okay, ma'am.
Okay. And put page number also, doesn't matter, but every page I want to see your name and your assignment title.
Okay, ma'am.
Okay.
Thank you.
Yeah.
Thank you, ma'am.
Okay. Yeah. Yeah. Thank